Ever find yourself wishing you could download information straight into your brain?
Like Matrix style?
Yeah, exactly. Well, we might not be there yet, this deep dive.
It's about the next best thing, really.
Neuromorphic computing. Essentially, building computers that mimic the human brain.
And the potential here is huge.
That's massive.
The paper we're looking at towards spike-based machine intelligence with neuromorphic computing,
It dives into you.
it dives into why that's so exciting.
Yeah,
Our brains,
they're incredible.
they are incredibly energy efficient.
It's really amazing.
We process complex information using roughly the same wattage as a light bulb.
Meanwhile, my laptop sounds like a jet engine, just checking email. So how does the brain pull off that energy efficiency trick? It seems like magic.
It's not magic.
Or is it?
Well, but it's pretty close.
Okay.
The paper breaks down 3 key ways. The brain's structure inspires this new wave of computing.
I'm ready.
First off, the sheer interconnectedness
Oh, yeah.
is mind-boggling.
It really is.
We're talking billions of neurons with trillions of connections between them.
Okay, so I'm picturing like this giant tangled web of neurons.
Yeah.
But it can't just be chaos, right? There's got to be some organization in there.
You're right. It's not random at all.
Okay.
That leads us to the second point, the brain's hierarchical organization.
Okay.
Just like those sophisticated AI systems that process information in layers, the brain has specialized areas that build on each other's work.
Interesting. So is that kind of like how some AI systems, they first learn simple features,
Yes.
then combine those into shapes,
Exactly.
and eventually recognize an entire object?
Exactly. Think of it like image recognition,
Yeah.
where the AI starts with edges,
Uh-huh.
then figures out shapes,
Right.
and eventually puts it all together to recognize, say, a face.
Okay.
Our brains have a similar system, but even more intricate.
Okay, so we've got the interconnectedness, we've got the hierarchical structure.
Hmm.
What's the third element that makes the brain such a powerful computer?
This is where it gets really fascinating.
Okay.
And it's all about timing.
Timing.
You see, in the brain,
Okay.
it's not just what's connected, but when those connections fire.
Interesting.
This timing element is crucial for processing information efficiently.
Hold on, timing. See, that's a bit different from how we usually think about computers.
Yeah.
Most computers, they just process data sequentially,
Right.
right? Like line by line in code.
You're right.
Yeah.
And that's where traditional computing differs drastically from how the brain works.
Okay.
Imagine you have a team working on a project.
Okay.
In a typical computer setup,
Yeah.
everyone's constantly active, even if only a few people are needed at any given moment.
Right.
Lots of wasted energy.
I see where you're going with this.
Yeah.
It's like having all the lights on in a house, even when you're only using one room.
Exactly.
Not very efficient.
Exactly. But with the spike-based approach inspired by the brain, it's more like each team member only springs into action when they have something specific to contribute.
I see.
If a neuron doesn't have important information to share at that moment,
Yeah.
it's essentially idle, saving tons of energy.
That's incredibly efficient.
Yeah.
It's like the brain has a built-in energy-saving mode.
Right.
So how do we actually translate this elegant system into a computer? So we're
Yeah.
talking about creating computers that operate less like computers and more like actual brains.
Right.
And that brings us to these spiking neural networks, SNNs.
Yes.
What are they and how do they capture that brain-like efficiency?
Well, SNNs, they're all about events happening in time, just like how you experience the world.
Okay.
Like it's not, a series of still images. It's a
Right.
constant flow, right?
Right. If I'm watching a movie, I'm not just seeing separate pictures. I'm understanding the action and the story as it unfolds.
That's exactly the kind of understanding SNNs aim for.
Okay.
Instead of processing data in a rigid, linear way,
Right.
they react to these spikes, these events,
Yes.
more dynamically. Imagine a network that's always listening, but only certain parts light up when there's something important in the data.
Okay, so it's less like reading a book
Mm-hmm.
and more like experiencing a live performance.
Yes,
Where the timing of everything is crucial.
precisely.
Yeah.
And that's what makes SNNs potentially revolutionary.
Mhm.
They mirror how our brains perceive the world,
Okay.
not as isolated snapshots, but as a continuous stream of information.
That makes a lot of sense.
Mhm.
But if SNNs are so great,
Yeah.
why aren't they everywhere already?
Well,
What's the catch?
you're right.
There's always a catch.
There's a big one, training SNNs.
Yeah.
It's tough.
Okay.
Remember how timing is everything?
Yeah.
Well, teaching a network to learn from those precisely timed spikes
Right.
is a whole new challenge.
It sounds like trying to teach a computer a language where the words are also musical notes.
Yes.
The meaning changes based not just on what you say, but how you say it.
You've hit the nail on the head.
Okay.
Because it's so complex.
Right.
Researchers are using different approaches.
Yeah.
One is called conversion. Essentially, they take an already trained AI,
Okay.
maybe one good at image recognition,
Right.
and try to convert it into a spiking network.
So instead of building a whole new brain from scratch, they're trying to translate the knowledge of a regular AI into the spiking world.
Exactly.
Interesting.
So like translating a book into a different language.
Yeah.
It can be effective,
Right.
but you're not teaching the SNN to learn directly from those time-based spikes.
So it's a shortcut,
Yeah.
but maybe not the most elegant solution in the long run.
Exactly.
What's the alternative then?
Well,
how do we teach these SNNs from the ground up?
That's the million-dollar question.
Oh, boy.
It's called spike-based learning,
Okay.
and it's where things get really interesting.
All right.
Imagine an AI that learns not just from the content of the information, but from the way that information unfolds over time,
Okay.
just like we do.
That's mind-blowing. It's like the difference between reading a musical score and actually hearing the music played live.
That's a great analogy,
Okay.
but as you can imagine, it's incredibly complex.
Right.
One of the biggest hurdles is that traditional AI training methods, they don't translate well to this spiking world.
Yeah.
They rely on continuous data, smooth changes,
Okay.
while spikes are these sudden, discrete events.
So it's like trying to use a wrench when you need a sonic screwdriver?
Right.
The tools just aren't designed for the job.
Exactly. Researchers are having to develop completely new algorithms, new tools,
Right.
tailored for the quirks of spike-based learning.
Wow.
It's like exploring uncharted territory.
Okay, so we've got the software side,
Yeah.
these SNNs, with their unique way of learning.
Right.
But what about the hardware?
Right.
Can our current computers even handle this kind of processing?
That's the other piece of the puzzle.
Yeah.
And it's a big one. The paper we're discussing highlights how crucial the hardware is for unlocking the true potential of SNNs.
I have a feeling we're going to need something more powerful than my old laptop.
You're not wrong.
Okay.
You see, the way computers are traditionally built, with the separation between the processing unit and the memory,
Okay.
it creates a bottleneck.
Okay, explain it to me like I'm back in computer science class, but maybe a little more exciting.
Think of it this way. Imagine a restaurant kitchen.
Okay.
You've got a fantastic chef, but the ingredients are stored miles away, and there's only a tiny door to pass them through.
That poor chef would spend more time waiting for ingredients than actually cooking.
Exactly.
Okay.
That's what happens in traditional computers.
Right.
The processor needs data from the memory, but constantly moving it back and forth slows everything down.
Okay.
It's a huge energy drain.
So how do we fix that bottleneck for SNNs? Do we need to build a bigger door for the chef?
In a way, yes. That's where big brain chips come in.
Hold on, big brain chips. That sounds like something straight out of a sci-fi movie.
Yeah,
Tell me more.
they're pretty incredible.
Okay.
We're talking millions, even billions of artificial neurons and synapses,
Wow.
all interconnected on a single chip,
Wow.
just like in a real brain.
No more tiny doorways. So these big brain chips can handle the unique demands of this spike-based processing. So these big brain chips are designed to handle all that spiking action. But how do they actually work? Is it like regular computer chips, just, bigger?
Not exactly. They use a completely different way of communicating information called address event representation, or AER. AER.
Okay.
Instead of constantly sending data back and forth, information is only transmitted when something changes,
Okay.
when there's a spike.
So instead of me constantly telling you, I'm still sitting here, I only speak up when I actually have something new to say.
Precisely.
Much more efficient.
It's like your eyes only sending information to your brain when something in your visual field changes, rather than constantly transmitting the entire image.
Right.
This is a major reason why the brain is so energy efficient.
That's incredible.
Yeah.
It's like the difference between a smoke signal and a 24/7 news channel.
Right.
Only crucial updates get through.
Exactly.
So big brain chips, AER, anything else we need to build these super efficient brain-like computers?
There's one more fascinating concept the paper touches on, beyond von Neumann architecture.
Okay.
It's a bit technical,
Right.
but the gist is this.
Okay.
Imagine if the memory in a computer could also do some of the processing instead of just storing data.
So instead of just being a storage room, the memory is more like a workshop where you can also work on the information directly.
A perfect analogy.
Okay.
This eliminates the need to constantly move data back and forth, which is a huge bottleneck in traditional computers.
Right.
And one of the key technologies that could make this possible is something called a memristor.
Okay, I've heard of those.
Yeah.
Like tiny artificial synapses, right? But how do they fit into all of this?
Imagine if your to-do list didn't just store your tasks, but each item also had a little bit of memory attached to it,
Okay.
reminding you how long it usually takes, how much effort it requires.
Right.
That's kind of what memristors could bring to computing.
Wow, that's next level efficiency.
Yeah.
It's like each piece of information comes with its own little instruction manual, so the computer doesn't have to start from scratch every time.
Right.
This is all so fascinating,
Yeah.
but it also seems incredibly complex.
It definitely is. And the authors of the paper, they stress that we need a collaborative effort
Yeah.
between those designing the SNN algorithms
Right.
and those developing the hardware.
It's like composing a symphony.
Exactly.
You need the music and the instruments to work together in perfect harmony.
Exactly. By understanding the strengths and limitations of both the software and the hardware, we can unlock the true potential of this technology.
So what's next? What are the biggest challenges researchers are facing as they try to make these brain-inspired computers a reality?
It's still early days,
Right.
but the potential applications are vast.
Yeah.
Imagine robots that can learn and adapt to complex environments in real time,
Okay.
or medical devices that can process and respond to subtle changes in your body's signals.
It's like taking the best of both worlds, the efficiency and adaptability of the human brain, combined with the processing power of computers.
Exactly.
Wow.
And that brings us to the heart of what makes this field so exciting.
Okay.
If the human brain, with its elegant use of timing and events, is the ultimate proof that intelligence can exist within this framework,
Right.
why wouldn't we try to build our machines the same way?
It's a question worth pondering.
It is.
What possibilities open up when AI experiences the world, not as a series of static snapshots, but as a symphony of events, just like we do? This has been an incredible journey into the world of neuromorphic computing. A huge thank you to our expert for guiding us through this complex and rapidly evolving field.
It was my pleasure.
And for our listeners, keep those brains buzzing. We'll catch you in the next deep dive.